Hi, questions in optics. Here is a textbook for optics. Problem 1. Two waves A and B have both a vacuum wavelength of lambda 0 equals 500 nm. They are started in phase and both propagate parallel to each other for a distance of 1 meter towards a screen. Wave A propagates freely through air, while wave B centrally transverses glass of water with an inner diameter of 10 centimeter and a wall thickness of 0.5 centimeter with Ng equals 1.52. Determine the relative phase difference data as I reach the screen. The problem comes from the textbook chapter 7, problem 7.6. And our problem here is changed to 500 nm, not 610 nm. The problem is illustrated by this figure. Problem 1. The wavelength in vacuum is lambda O equals 500 nm. The distance between the starting line and the finishing line is d equals 100 cm. The wave B propagates freely through air. For air, Na equals 1. The wave A transverses glass of water with an inner width 10 centimeter and a wall thickness of glass 0.5 centimeter, illustrated in the textbook figure P7.6. Then we can get the optic path length for A and for B. Wave B propagates through air. So OPLB equals this one. The wave A passes in air, given by this one, and passes in water, given by this one, and passes in glass, given by this one. So it equals this value. Then the optical path difference is given by this value. The relative phase difference in the finishing line is found to be this value. Problem 2. Natural light of 1000 watts per meter square is incident normally on a stack of ideal polarizers. The transition axis of the signal lies on the 30 degree to that of the first, the third on the 60 degree, and the fourth on the 90 degree. Determine the irradiance after the stack. The problem comes from the textbook in chapter 8, problem 8.28. Here, our problem is changed to 1000, not 300. Problem 2. The problem is illustrated in figure P2. A randomly polarized light I0 passes those four polarizers. This line is the transmission axis of the first polarizer. Signal here is 30 degree, and the third 60 degree, the fourth 90 degree. Since I0 is randomly polarized and the polarizers are ideal, when the light passes to the first polarizer, we have the polarized light I1 equals half of I0 equals this value. Then the light passes to the second linear polarizer. We have the polarized light I2 equals I1 times cos square 30 degree. Then the light passes to the third polarizer. We have the polarized light I3 equals I2 times cos square 60 degree minus 30 degree. Finally, the light passes to the fourth polarizer. We have the polarized light I equals I4 equals I3 times cosine square 90 degree minus 60 degree equals this value. Thanks for watching. Bye.